talk about momentum and impulse. This is a very useful approach in physics when you have a system that has a massive object that undergoes a rapid change of velocity because of an applied force. We'll start by defining the impulse-momentum principle, and along the way we'll have to define impulse and momentum, and then we'll utilize it and analyze physics problems using this approach. We'll do this for a simple applied impulse and then for the problem of a bouncing ball. Let's start by deriving the impulse-momentum relationship. We'll start with Newton's second law. Sum of forces equals mass times acceleration. Notice this is a vector equation. We can write acceleration as a change in velocity with respect to time. We could bring the mass inside that derivative if we wanted to, and write sum of forces equals ma equals dp dt, where the p is the momentum, defined as mass times velocity. Let's work with a one-dimensional example, just in the x direction. Here we have m dvx dt equals the net force as a function of time. We've written this as a scalar equation because we're only in one dimension. Now let's do separation of variables. We bring the dt to the right and then integrate. For the left side of the equation, this is an easy integral to do. We just have mvx final minus mvx zero equals the integral from t0 to t final of the net force dt. On the left side, you can see that that's just the change in momentum, because momentum is defined as mv, and the term on the right side, we're going to define that as being the impulse, the integrated force over an increment of time. For complicated interactions, sometimes we'll just use the average force instead of integrating over the time. So delta px equals force average times delta t. Remember, when we developed the work-energy principle, it looked very similar to this. Change in kinetic energy equals work, which was the force integrated over a distance. Here we have change in momentum equals impulse, which is force integrated over time. Let's work a sample problem. A steady 3.2 Newton force impacts a 1.2 kilogram rock for 0.65 seconds. If the rock was initially moving to the right at a speed of 1.3 meters per second, how fast was it moving just after the impact? We'll start by drawing a diagram and making assumptions. We'll assume, since we have a steady force, that it's a constant force over the whole time. We'll treat our rock as a point object. We'll say there are no other forces acting on the object. This diagram shows what the force looks like over that delta t. Now we'll define our known and unknown variables. We know the force, we know the mass, we know delta t, we know the initial velocity v0, and we want the final velocity. We start with a general equation. The change in momentum equals the impulse, and then we'll specify the equation for our system. We'll solve it symbolically in terms of given variables and analyze our result. For our system, change in momentum is mv final minus mv0, and we'll just take the average force times delta t. That works well for our function. Solving that for V final, we get V final equals average force times delta T plus mv0, all divided by the mass. Plugging in our values, we calculate that our final velocity should be 3.0 meters per second. Let's start by looking at the units to make sure they make sense. Force is kilogram meters per second squared times delta T. Adding on the mv0, that's kilograms times meters per second, dividing through by kilograms, we see that our final velocity has units of meters per second. That's good. Also, let's look at order of magnitude. Our final velocity is 3.0 meters per second. Seems like a reasonable velocity. It's more than 1.3 meters per second. That's good because we had a force acting on it to the right. And it's about the right order of magnitude. It isn't something in milliseconds, or it isn't something in years or something like that. Now let's analyze result by looking at special cases. I'm going to rewrite it a little bit differently to make it simpler to analyze. In this form, we can see that the force per mass, if that's larger, then we should have a larger velocity. That makes sense. Force per mass is acceleration. Larger acceleration would give larger velocity. Also, with the same amount of force per mass, a bigger delta T would give us a larger final velocity as well. That makes sense. If the force was impacting the object for a longer period of time, you'd expect it to be moving faster. And finally, a larger initial velocity gives it a larger final velocity. That makes sense as well. If it was moving faster before the impact happened, then it should be moving faster after the impulse as well. Let's do another example. A 0.15 kilogram ball is dropped from rest from a height of 1.25 meters, bounces back up to a height of 0.80 meters. If the impact took 0.10 seconds, what was the average force exerted on the ground by the ball? We'll start with a diagram and assumptions. We'll define known and unknown variables. Our general equation, we know we're going to be working with momentum impulse. Then we'll specify that equation for our system, solve symbolically in terms of given variables, and analyze our result. Let's start with a diagram. We see that there are actually 4 points of time that are interesting. Our initial time, when the ball's at rest at some height h0, then the ball drops down. It's moving when it hits the ground and squishes some at t1. At t2, it has v2, which is upward. It's bouncing back up. And at t3, it's bounced back up to its second height, h3, which is less than h0. Drawing out our diagram first helps us to label our variables. We know the mass, we know h0, we know h3, and we know delta t. Here delta t is t2 minus t1. We want the average force. We start by specifying the equation to our system, mv2 minus mv1 equals force average times delta t. It's pretty simple to solve for the force average equals the mass times v2 minus v1 quantity divided by delta t. We don't know v2 and v1, so we have to find them somehow. We could use either kinematics or a conservation of energy approach. I'll use a conservation of energy approach here. The potential energy at time 0 plus the kinetic energy at time 0 equals the potential energy plus the kinetic energy at time 1. Our initial potential energy is mgh0. Object is at rest, so we give it k0 equals 0. At time 1, its potential equals 0. We'll let that go to 0 at the bottom. And then plus 1/2 mv1 squared. This allows us to solve for v1 equals root 2gh0. Now notice I have a plus minus on it. I have v1 going in the downward direction. So I'll take upward as positive and let v1 be minus root 2gh0. The treatment for time 2 to time 3 is exactly the same. Initial potential plus initial kinetic equals final potential plus final kinetic. Here we have the initial kinetic energy is 1/2 mv2 squared, and at time 3, the potential energy is mgh3. The object is at rest, so it has kinetic energy of 0. Solving for v2, we get v2 equals a positive root 2gh3. Now, if we substitute these expressions into our F average equation, we get the F average equals the mass times root 2gh3 plus root 2gh0. Notice that minus sign matters here. Take that all over delta T. Now I just plug in my values for each of these terms and calculate the answer to be 13 newtons. It seems like a reasonable order of magnitude for a force of dropping a ball onto the ground. We can check units. Kilograms times root meters per second squared times meters divided by seconds. That would be kilograms times root meters squared per second squared, which is meters per second, all divided by seconds, which gives kilograms meters per second squared, which is newtons. So we're happy with that. Now let's analyze the result for the special cases. We see that a larger mass means that a larger average force was exerted on the ground. That makes sense because larger mass means that there's more momentum that has to be changed. We also have little g in the numerator, so a larger gravitational acceleration means a larger force. That makes sense. If I drop something and it's moving faster at the bottom, it's going to hit the ground harder, so it'll have a larger average force when it impacts. Notice both heights also give a larger average force. So h3, that makes sense. The higher I lift it, the larger the force is going to be when it hits the ground. And also, the larger the height that it rebounds back up to, the larger the average force. That makes sense because then the ground is pushing on it harder as it's going back up. Delta T is in the denominator, so a larger time means that it would have a smaller average force. That makes sense too. If the ball hit the ground for a larger amount of time, but with everything else held the same, then the force would have been smaller because it would have been spread out over more time. So we've looked at momentum and impulse. We defined the momentum-impulse relationship. We define momentum as the mass times velocity. Momentum is a vector quantity. Impulse is the integral of force over a certain amount of time. And the relationship between the two is a change in momentum equals the impulse. We applied this to two different problems, a bouncing ball, after we did just a simple applied force problem. That's it for momentum and impulse. Thank you for coming, and come back soon.